session fourth of this second day faculty development program. We have a youngest speaker, that's Dr. Walke. Dr. Walke has obtained his PhD from Naples University, Italy, in collaboration with the National Council for Research, CNR, Italy, in 2010. And he worked on nanoscale squid devices for high sensitive nanoscale applications under the supervision of Dr. Granata. Before joining for PhD, he worked in National Chemical Laboratory, Pune, under the guidance of eminent scientist Dr. Vijay Manoran, our earlier speaker, followed by South Dakota State University, USA, at Advanced Center for Photovoltaics. During the postdoctoral training, as a prestigious Marie Curie experienced researcher with Luders, he developed high K dielectric materials using oxide nanoluminates for capacitive devices. He worked as a RA 2012 to 13 and obtained Best RA Award in Inter-University RMC at Department of Physics, University of Pune. He has awarded UGC Raman Fellowship for 2015-16 to pursue his postdoctoral training in University of California, Berkeley, USA, under the guidance of Professor R. Ramesh, former director of National Nano Initiative Program, USA. Since he joined Mumbai University in 2013, he has established a research group working on energy materials, thin films, and nano micro devices in NCNNUM. He published his work in reputed international journals. Greater than 50 research articles are there, and couple of books to his credit. He is a reviewer of several reputed journals. He is a member of various national and international societies. Recently, he is writing a science article in Marathi for spreading awareness of science in the society. His research in energy storage, especially fast charging, lightweight, and long life batteries, has attracted media attention. Dr. Walke is a member of Board of Studies of Nanoscience in Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, Amity University, Mumbai, and University of Mumbai. He is a member of expert committee constituted by Government of Maharashtra and Marathi Nirmuti Mandal for nanoscience subject. He is a recipient of Young Scientist Research Grant from DST and Reviewer Recognition Award in 2017 by Department of Energy, BARC, Mumbai. He actively participated as a resource person in the international bilateral programs such as Indo-France at VIT Chennai, among the top selected people across the couple, and Indo-Egypt conference of a DST hosted by IIT Mumbai. He is now working as a faculty at National Center for Nanoscience and Nanotechnology, University of Mumbai, Mumbai. So I request Dr. Walke to take a charge of this session. He will be talking on most of the microscopic techniques because he is from the National Center for Nanoscience and Nanotechnology, where almost all material characterization instrumentation is available. Okay, I request Dr. Walke to deliver his talk. Introduction to microscopy and effective tool of nanomaterials characterization. Okay, over you.
Thanks, Professor Bhaskar, for such a nice introduction and quite a lengthy introduction. First of all, let me thank organizers, Professor and team Babu University for bringing me here on this platform to interact with all of you through this kind of program. So it's my pleasure to be here today and present some of basics of microscopy in front of you. I'm sure that since last 2 days, this is the second day, and since yesterday you have been bombarded by a lot of nanomaterials, lot of applications, and so many different synthesis and characterizations tools. And just now, Professor Vijay Mohan has light on a lot of nanomaterials and their applications, especially in energy. And therefore, I decided to just have another perspective about nanotechnology and just look into the basics of the microscopy, because if I'm not wrong, there are many master students also participated in this program. So keeping focus on the students, I have prepared this presentation very simple and try to make it as a basic introduction about microscopy and its application towards nanomaterials characterization. So I would be very glad if some of you probably know most of the part of this microscopy basics, but if you can take at least one or two takeaway points today, then I would be very. I think that this talk is become fruitful, right? So let's have a look on the today's presentation. So here are outline of my presentation. With the permission, shall I put up the video so that I can get more bandwidth of my this presentation? I'm not sure whether I can do that or not. Okay, so I hope this presentation is quite visible to all of you.
Yes.
So here
Yes.
are outline of my today's presentation. Let's first I will introduce about the general microscopy, and later we will see just something about the fundamentals of the microscopy people are using, and this fundamental is required knowledge to get a good imaging using the microscopes. Further, we'll see the basics of optical basic working principle of light and optical microscopes and their application in taking the micrographs of different for different applications. We'll see the electron microscopes, why there is a requirement of the electron microscopes. And more famous electron microscopes are scanning electron microscopes, transmission electron microscopes. So we'll see a bit about the scanning electron microscope assembly and working principle and how these images can be acquired, what are the problems coming in those imaging, and how we can overcome those problems. So this can be majorly focused in this presentation. Further, there will be the probe microscopy. And probe microscopy is the different than the electron microscopy, where we use the physical probe to image those nanomaterials also. So in the probe microscopy, there are the various modes, but we try, if time permits, we'll try to look into the atomic force microscope and scanning generic microscope, etc. And then we will summarize the presentation. Okay, so what is the microscope? Since the ancient age, we have seen that there is drastic development from this sort of, let's say, binocular lenses and use of the binocular lenses to maximize the images, smaller image into the larger images. And since then, there is a continuous development of the microscope. We have seen here, there is a consistent development. And nowadays, we have come up to these kind of advanced microscopes over here, right? And further on from the optical microscopes, we have moved towards the electronic microscopes. So this is the drastic improvement in probably the last century is happened in case of the microelectrodes or in case of microscopes, right? So what would be the microscope? Microscope word itself suggests, the meaning of that. Micro, it means very small or small at micro scale. Everybody knows about that. And the scope is like to look at it, right? So how to look at the micro scale level images or microscope level specimens, how can we look into, right? And that tool is known as a microscope. So here you see the picture, photograph of the cell that has taken by the microscope. And these kind of pictures taken by those microscopes are called as micrographs, right? So this getting a good micrographs and more understanding about the invisible world is the major focus of that microscopy, right? So microscopy is mainly used for these kind of applications. So these microscopes nowadays has become one of the major tool for the research, especially in scientific field, especially those are biological people. They are regularly using in their high school classes or undergraduate classes to look into the plants and animals and tissues and all those things. They use regularly the microscope. But that microscopes invention has started since 1590, right? So first compound microscope were established, and that has helped someone to find out more about the life sciences, right? So to explore the world of invisible things, this first compound microscope has played a significant role in this. Significant role in this. So the how the historically the microscope has been transformed. Let's say in 1519, probably 1590 to 1595, since the discovery of the first compound microscope built by Zacharias Janssen, right? Since then, in 17th century or in 1680, so Anthony von Leeuwenhoek, who was awarded the fellowship of the Royal Society for his advanced microscopy done by arrangement of different kind of lenses. And since then there are in 1910 we have found out the Leeds which has built the photomicroscope in 1910. So that Leeds has developed the photomicroscope. Since then there is a drastic evolution happened since 19th century, and we have found in 1934 the Fritz Hennig invented the phase contrast microscopy. So we have to just change the phase, and we will find that there is good imaging processes can happen with the phase contrast. So this in 1934 has been invented. Later on in 1955, so the Nomarski who has invented the differential interference contrast microscopy, and since then further the Zeiss introduced the universal mode. Nowadays the Zeiss lenses are more famous in the world, and they have started their journey in 1960, right? Since then further the video microscopy, and then in 1994 GPF, and now in 2000 onwards we have found that there are super resolution light microscope has been introduced. And recently many Nobel Prize has been owned by this kind of microscopy world, right? So let's have a look on this kind of Nobel Prize in the microscopy. So why this microscopy is very important, right? So as people are getting the Nobel Prize for the development of microscopy, then we can easily understand how important this microscopy world for the scientific community. So in 1986, the Nobel Prize in Physics was given to the development of microscope, right? So it was divided between three scientists, but one half of the award was given to the single scientist called Ernest Ruska. For his fundamental work, he has done about the electron microscope, and he has designed the first electron microscope. And therefore, he got a half of that prize in 1986. Then after that, the Kurt Binning and Heinrich Rohr for their designing of the scanning tunneling microscope. So that is STM, that is a probe microscopy, and first half was given by the electron microscopy. So that has been given in 1986. Yes, am I audible? I hope I'm audible to all, right?
Yes, you are audible.
Yeah, thank you. So further, let's see. The recent Nobel Prize was given in 2014. Nobel Prize in Chemistry was given to the Hell and William Warner. Right? What they have done is they have just introduced the optical microscope in new dimensional using the fluorescent molecules. Right? So this was the new angle of the microscopy, and therefore they have received the Nobel Prize in Chemistry in 2014. Recently, in 2017, the Nobel Prize in Chemistry was awarded to the Jacques Dobchet and Jopping Franks, Richard Henderson for their development of the cryo-electron microscopy. So the cryo-electron microscopy, if you go to the YouTube and so on, you can easily look how this cryo-electron microscope can work, right? So this cryo-electron microscope, especially used for, the two important things. It has very simplified way improve the imaging of the biomolecules, because the biomolecules are very sensitive, and electron microscopy, using electron microscopy to image the biomolecules are very difficult. So this kind of a cryo-electron microscopic development was done, and that helped us to do the imaging of the biomolecules, and therefore it has given a Nobel Prize in 2017. Though this work has been invented long back, it has given a Nobel Prize in chemistry 2017. So let's have a look on the basic optical microscope. So until and unless we understand the basic optical microscope, it's very difficult for us to get a read of or get a clear understanding about the electron microscopy or probe microscope. So how this optical microscope works? So basically, the microscope is an array of the two important lenses. First one, there is one focal plane from where focal plane where you want to focus or where your specimen and sample is, and then image plane is like where you are seeing from which side you are seeing that. So there are the two planes. One is your eye where you are seeing, and another is the focal plane where you want to focus. So in between those two planes, there are the two lenses arranged. One is objective lens and another is the tube lens, right? So this objective and tube lens arrangement is very important in order to get the microscopic or micrograph images, right? Okay, so this is the importance theoretical microscope, theoretical understanding of microscope where array of the two lenses are there. Let's have a look on the important part is objective. Here we see, a normal microscope, we are using this kind of objective lenses. And here you can easily see the Nikon and Nippo Japan companies. They have developed this kind of objective lenses. And on the objective lenses, we see there are the different important specifications has already been written. Those specific important signals which are giving, let's say for example here in 60x, right? So which can show us the lateral magnification, how much lateral magnification this sort of objective lenses can be do. Then further is the numerical aperture is one of the important parameter which has already mentioned on this microscope. So further, same thing we can see here, but here there is a oil, right? So the immersion medium. So they have used the immersion medium in this kind of the objective lenses. So why these things are very important? Why this important information or parameters has been written on the objective lenses? So, and once we go to see the magnification and numerical aperture, what are they? So until and unless we know about these things, it is very difficult for us to understand why these values are very important when we are using any objective lenses. So let's have a look on those specific values first. So what is the magnification? So magnification is nothing but the measure how much larger a microscope cause an object to appear, right? So how big image you can visualize, right? How you can maximize the image and visualize it. So set of lenses we have to arrange in a microscope in order to magnify the image, right? So this magnification, which can be defined by magnification by the objective lens and as well as the magnification of eyepiece. So we are using the one lens at an eyepiece and one as objective lens, right? So the magnification of the both lenses, which can multiply together, and we can find out the total magnification of the given microscope. But keep in mind, this magnifying the image doesn't mean that the resolution, right? So how big you are making the image or how maximizing image you can see, that doesn't give you the exact resolution of that particular microscope. So resolution is something different. So what is that? Let's have a look on the resolution. What you mean by the resolution? So resolution, here you see there are the ABC3 images, and here is the single point, let's say, right? Single point which can clearly seen and the fringes around that single point. But if you have 2 points very close together, right? And the separation of the 2 points can be easily seen by that particular microscope, right? So then what is the minimum distance between these 2 points? We can easily look by our microscope or easily see by our microscope. What is the minimum distance we can separate the 2 points, right? And that minimum distance is nothing but the resolution, right? So here in the C figure, you see there is no separation can seen in these 2 dots, and therefore the resolution is not so good, right? So the resolution, smaller the value of this distance between the 2 points, then we can see the higher resolution power of the given microscope, right? So in order to have the better clarity and detail imaging, we need to have very good resolution, right? So we'll see further how the resolution can be improved in the different systems. But first of all, just understand about the resolution, because we are using those words later frequently: magnification and resolution. Further, we had seen one important thing is numerical aperture. So NA value on that particular objective lens. So what is that numerical aperture? So numerical aperture is nothing but an estimation, or it has to estimate how much light from your sample is collected by given objective, right? So here you see this is the simple figure which shows that we have the glass light, and over that we have the cover slip. Then sometimes we use the oil, there was written by oil immersion, so the immersion technique, oil has been used. So these have different refractive indexes, right, or air, right? So here n is represented as the refractive indexes, and these alpha 1 and alpha 2 are the incident angle, right, angle of incidence of that particular beam or illumination. And once we know the incident illumination angle, and once we know the refractive index of the given system, we can easily calculate this numerical aperture value. And this numerical aperture value also plays a very significant role in resolution, right? So here this numerical aperture can be calculated by using the total refractive index of these different slits and slides we have been used for these objective lenses, and sine of that particular incident angle. Okay, so this is the important parameter of the numerical aperture. So how can we improve the resolution? So higher the numerical aperture of your lenses, you will get much better resolution of your specimen, right? And here from this diffraction law, you can see the d is equal to 0.5 lambda upon n sine theta, where we can consider this d as a resolution, let's say. Then your lambda plays a very significant role. The wavelength of light used to see that kind of specimen or take a micrograph, this lambda value plays a very significant role. As we know, n sine theta, the aperture value, is also important. So that aperture and the wavelength, these two are a very important parameters which can easily find out the resolution value. Okay, so how can we improve the resolution? Just magnifying the image doesn't mean that it shows the good resolution, right? So the numerical aperture, which is also the important parameter, important part, which will give us an significance about the resolution. So here you see, if we improve this numerical aperture here, so here you see the diameter of this incident beam here, and this is increased, and further it is increased. So that means you are increasing the numerical aperture of your lenses. And if your numerical aperture was improved and it has focused on the sample, you will find out here these images, right? So if your numerical aperture goes on increase, you will find out the sharp images you can see here, right? The sharpening of the image is possible with increasing numerical aperture, right? So it means in order to have the good resolution, the numerical aperture should be bigger in this case, right? And that will let's say if you see here the two images, one and two images. So this one image and this second image, they're two small dots and which are separated by the very tiny distance. So in this case, we need to have the very good aperture, very high aperture, to get this kind of separation. Here we cannot see the separation of the two small dots just by using the low aperture, right? Lower numerical aperture. But if we increase, we can find out these are the two dots separated by the small distance, can be easily identified by improving the resolution of the system, right? So these are the very important parameter or basic fundamentals which need to know before doing the microscopy. So in the microscopy, basically the two different microscopy. For example, the light microscopy people have been using for the micron scale, and especially the biological studies. A lot of biological studies can be done by using this kind of the light microscope, right? But if we want to have the more resolution and go to the lower dimension, we can go to the electron microscope. So let's have a look on what are the light importance of the light microscope first, and then we'll go to the electron microscopes. Okay. Okay. So what are the light microscopy? Light microscopy or optical microscopy, where we are simply using the incident beam, is nothing but our visible light, right? So we are using the visible light as an incident beam. Later in this optical microscope, we are using the glass lenses. What would be the advantage of having this kind of microscopy is, usually people in biological sector are using this microscope for the looking at the living cells, right? And they want to watch the cells which are mitigating or dividing. What is the momentum of that particular cells? They can be observed under the different light microscopes. So this is the general principle. I just don't want to go much detail about this principle because everybody knows about the principle of optical microscope, right? Where we can pass the light from the medium and one medium to another, and the light gets bent. That is called as refraction. And because of this bending, the light slows its speeds, and bending of light is determined by the refractive index. As we have seen before, the refractive index plays a significant role in your numerical aperture value, right? Okay, so let's have a different types of the light microscope. So there are the different modes of the light microscopes can be used to get rid of good microscopy. So this microscopy, in the simple word, is sort of the photography, right? Same like our photography. In the photographs, we are just focusing and aligning the lenses to get a better objects, and then we are capturing those images, right? Same thing we are doing in the microscope. So microscope for me, or for the lemon, microscope is nothing but the photography at the lower scale or micro scale, right? So there are the different modes, same like our camera. We are using the different types of light microscopes, scope mode. For example, people are using the four important microscopic modes. One is a bright field light microscopy, phase contrast light microscopes, then dark field and fluorescent light microscope. So bright, dark field, and phase contrast and fluorescence, why they are important? Because depending on the sample, these kind of modes are giving the highly high specific images of that particular specimens, right? So here there is one of the examples. So contrasting techniques. So depending on the sample, the contrast is going to be changed. So individual mode will help us to understand more about the system depending on the different mode. For example, here you see the fibroblast which is grown in the culture. So that fibroblast here grown in the culture here. So these fibroblasts can be measured seen by the different techniques. For example, here see this is the bright field image. So in the bright field image, you can come to know, there is a fluorescence going in the structure. Further, you go here and see the phase contrast. If you change the phase contrast and took the images, you can clearly see here the separation of this, right? So further, the dark fields. In the dark field, your whole background becomes the dark. In the bright field, your background becomes the bright, right? And how this illumination or how this microscopy of that fibroblast will see. So here you can only see the fibroblast. You cannot see the cell around, culture around this, right? And here DIC image as well. So after seeing all these four images, we can clearly understand what are the importance of these different contrasting techniques, right? So these contrasting techniques need to be understood very thoroughly so that we can easily get enough information from this kind of microscopy, right? So let's have a basic fundamental about what is the bright field. So bright field, usually what happens, the light which transmits through the sample, some of the light get absorbed and some get transmitted through the sample. So what is the major application? Here you see the cross section of the sunflower root, right? The sunflower root image can be seen by using the normal microscopes, right? So here you can see the piece of the artificially grown skin, right? By using the bright field imaging techniques or bright field mode of that microscopy. And the application of this bright field is, right, for the specimens, for example, if your specimen gets contrasted by the dyes, then it is very difficult for you to visualize those particular specimen inside the dyes or organic coatings, right? So in that case, the bright field imaging help us to get the images, right? So if we have the very little contrast, right? So for example, in unstained specimens, in that case, you can use the bright field imaging, right? So with this, what happened in the bright field, usually the background is a bright, right? And if the background is bright, then our human eye can will require the local intensity fluctuation, right? There is the local intensity fluctuation, which will be around 10 to 20% to able to recognize the objects, right? So this is the basics of the bright field techniques, right? Let's have a, this is general type of the classroom microscopes that we'll see later. So this bright field imaging and dark field and contrast that we'll see in a bit. But before going to that, let's have a look on this normal microscope, what we are using in the laboratory. Here we have the eyepiece, first of all. So this eyepiece plays a very important role, as we have seen about the resolution, right? So, and this kind of eyepiece is also known as ocular, which contains the first lens that we are looking into, and the maximum magnification we can do by using that particular eyepiece is like 10 times, like 10x. Okay, so this is normal eyepiece, and there is another objective lens. So this objective lens here, a lot of objective lenses given with a different specification. For example, your magnification, for example, your aperture, and all those things helps us to understand the resolution of this device, right? So we have to combine both eyepiece as well as our these objective lenses in order to get a good magnification, right? And that magnification and resolution. But what is the maximum magnification we can get by the objective lens is around 40 to 400 times x, right? So these are the two important components of the normal microscope. So as we have seen the dark field imaging, what about the phase contrast imaging techniques? So in the phase contrast imaging, you see here in this figure, here you have, these are the incident light, right? So incident light is I0, which is completely out of phase with the transmitted light. Here are the transmitted lights of I, right? So what happened if we slowly move this light or scan this light over the different part of the sample? What we observe is that the phase of the light need to be synchronized with the interference lens to get a highly great contrast image. For example, here you see, here is that particular interference lens has been added, and these are these different lenses which has to add in between the column. And then once it's synchronized by the interference lenses, we can find out this phase ring. So when it is aligned, you cannot see here the continuous flow of this brightness as well as this green part. But here, when it is aligned, you will see the continuous bright ring, which is showing the interference around that, right? So that is interference pattern around. It means the phase contrast, so phase of the light will be synchronized with the interference lenses, and therefore we can get a very high contrast image of that, right? So this is the important technique of the phase contrast as well. Okay, so this is, as we have seen some of the images before. So now let's have a look on the phase contrast images and how, just get a feel about how phase contrast is very helpful in case of the microscope, right? So here you see the bright field imaging, where this first image is showing you the bright field imaging here. But if you have not having the good phase synchronization, you can see here the wrong phase stop, where it is very difficult for you to see the image very properly. But at the same time, if you have very right phase stop, then you can easily see this image, which is completely overlapping with the bright field imaging, right? So it means this phase contrast is commonly used contrasting technique, especially all tissue culture microscopes and especially the time-lapse microscopes. They are set up for these kind of the different phases, right? So this is another important feature of these microscopes. Further, let's have a look on these applications. So somebody can use these applications for any other things rather than plants, animals, or let's say studying the microbial mobilities and locomotions in the biological samples. Also, certain microbial elements, for example, the bacterial endospores, how bacterial endospores can be looked like. So these are the different applications in the biology, as well as we can use those applications in case of inorganic and organic materials as well. So further, we have to go towards the dark field. What is the basic principle of the dark field actually? So let's have a look. The illumination rays of the lights right here are directed through the sample, right? But they have to go through from the side part here. So you see here the side, where we are putting the dark disk into the condenser lenses that are hindering the main light beam, principal light beam entering into the object. Okay, only the light scattered by your structure will enter into the objectives, right? So it means you have to prepare the dark shadow brightness at the background, and only the scattered structures signals lights can come to your objective. And here you can see the bright field imaging at the right side. You can see the bright field image of symbiotic diatomic colony, right? Symbiotic diatomic colony, you see there is the different colors, right? And here at the center, at the corner, you can see the bright field imaging, and which is not properly visible. But here you can see these are the different color illumination just because of the dark field background, and it will be very easy for us to individually identify the part of this particular symbiotic diatom colonies, right? So why people use this kind of the dark field imaging usually? Because they have to look into the diatoms, and or if there are unstrained or colorless specimens available. So in that case, it is very difficult for us to use the bright field imaging because there are colorless specimens, and for us it's very difficult to visualize them in the bright field imaging or normal imaging, right? And therefore, people are using the dark field imaging to understand those unstrained or colorless specimens, right? So this is another important mode of the dark field, and the application of that particular dive is it is used to visualize the internal organ of the given different larger cells. For example, eukaryotic cells, right? In the eukaryotic cell, there are a lot of organs inside, and it's very difficult to separate it out, right? So as we have seen in the previous image, the different colors can identify the different organs of that particular cells. Further identification of the bacterial cells, right? Having the different steps, like Treponema pallidum. Treponema pallidum, that is causative agent of the syphilis. So this is another bacterial applications. This kind of dark field imaging can be used. So this was just about different modes of the light microscopes. These are the different modes of the light microscopes, as we have seen, and understanding of the modes of the light microscopes or optical microscopes can be also applicable to the electron microscopes, right? And those light microscopes had some limitations. And what is the advantage of having the electron microscope, right? So light microscope usually good for the biological applications, but if you want to go really to the nano world, this light microscope has limitations, right? So let's have a look on these electron microscopes. So there are the different imaging methods, as we have seen this light or optical microscopy, right? Already we have gone through the light and optical microscopes imaging method, but here you see at the right side the SEM micrograph, right? So this SEM micrograph, to get such a beautiful SEM micrograph imaging, some of the important aspects need to be known to the students as well as who are operating the system and the users, because users have to also know that how we can get more or highly resolved SEM imaging, better imaging, right? So whatever the image you capture from your SEM, whether you are satisfied with that image or you are expecting something more to be happening in that, and in order to get that high resolved imaging or very high nano world, then there is some fundamental or key points need to be known that we will see in a minute or so in our further presentation. So there are the two electron microscopy. So first of all, the question arises, what is the limitation of the light microscope? what would be the advantage of electron microscope? What would be the further limitation of the electron microscopes, right? And electron microscopes, why there are the two different electron microscopes? For example, the scanning electron microscope, popularly known as the SEM, and transmission electron microscope is known as a TEM. So why these two different techniques are required? Right? So what are the use of those two different techniques for the characterization? I'm audible to all, right? Is there any query?
Sound is very clear. No issue.
Okay, fine. Okay, so the electron microscopy, for example, SEM and TM, why there are the two different electron microscopies are there? And then scanning probe microscopy, what is an advantage and disadvantage of having the scanning microscope, scanning probe microscopy, for example, STM and TM. So that we will see during the course of this next 1.5 hours and so. So let's have the let's see the resolution in it. What is the limitation of your microscopy, optical microscopy? So general light microscope can maximize or magnify the image 500 to 1500 times x, right? So this is the limit of that light microscope. The magnification is one restriction. Another restriction is the resolution. So resolution, we cannot go more than 0.2 micron, right? So below 0.2 micron, we cannot see by using the normal light microscope, right? So we cannot go really to the nanoscale, and therefore it is called as a microscope, light microscope, which can go towards the micron level. But how this resolution can be improved? What is the important factor for the resolution, or on what resolution is depending on? So first of all, the wavelength of the illumination or wavelength of beam. So the lambda value. So the wavelength of incident light or incident ray is highly responsible for the resolution, as we have seen already in previous cases when we are talking about the numerical aperture, right? But the numerical aperture of the lens, what you are using for this particular optical microscope, so the numerical aperture is also have some limitations, and therefore the total resolution is restricted to the micron. So in order to go to the nano world, or to look into the nanoscopic images, or I can say this electron microscopy, instead of electron microscopy, we should talk it as electron nanoscopy, right? Because we are going towards the nano world with the electron beam. Only optical beam comes up to the microscope. But at nanoscopic level, we are taking electron beam towards the nanoscopy. So sometimes I may use the word about nanoscopy rather than the microscopy. So this resolution depend on these two important factors, lambda and Na. So in case of, let's say, electron microscope, what happened to the wavelength of electron, or how we can tune the wavelength of the electron? So first of all, electron wavelength is depend on 3 points. First of all, the electron mass, which is always constant, we cannot change it. Electron charge, that is also the constant, we cannot change it. But what we influence is the potential difference to accelerate the electron. So what is the potential difference we are applying to generate those electrons, or pushing that electrons from the column of that electron microscope? So that particular potential difference plays a very significant role to tune this wavelength, right? So if you tune this wavelength, and this wavelength is in picometer, that is electron wavelength is around the picometer, and that is much larger, much smaller than this optical wavelength, right? Optical wavelength is 400 to 600 nanometers, right? But if you go to the picometer level by using the electron, then your resolution will improve drastically, right? And this is the major concern about the electron microscopy. Why electron microscopy is important? Because the wavelength plays a very significant role, and electron beam wavelength can be tuned by using the potential difference to accelerate the value. So let's have a look on scanning electron microscope, the basic principle of the scanning electron microscope. What happened here? You see here the schematics at the right side, where you see here the emitter or the electron gun, which produced the electron beam or extracted the electron, and those electron can pushed by the electropotential difference, and they have passed through the columns, and those columns are having the condenser lenses, deflection coils, then final lens, and ultimately it come and interact with your specimen, right? So To understand the scanning electron microscopy, first of all, we need to understand the different segment of this, right? So the wavelength, what we generated for this electron beam, right? So how we can tune the wavelength. So that is depending on what sort of electron gun you have been used, right? What is the applied potential difference you have used here in this kind of electrochemical microscopy. Further, these condenser lenses and those deflection coils and other lenses, so instead of using the optical lenses, as we are using the electron beam, it needs to be used as electromagnetic lenses, right? So the electromagnetic lenses are also generating the electric field, and they are pushing this electron through the column towards the specimen. Okay, so this is as simple as that. Just instead of the optical microscopy, we are using the electron beam to pass through, right? And then it is interacting to the specimen. And what happens if the electron interacts with the specimen or interacts with the matter? And if electron interacts with matter, what sort of signals we are getting? So here we can easily see the electrons which can taken by the detector, electron detector, and those can be amplified further in order to get an image. So after amplification, those signals can be converted into the image, and that image we can capture, right, in the SEM. So this is how the basic principle of SEM works. So what happened first is electron beam strikes to the sample, right? Then electron get penetrated to the sample or surface of the sample. Then there is an interaction of electron happen with the sample, okay? And then we can get either emitted electrons or photons from the sample. Those can get collected, detected, and converted into the image. So this is the very simple technique scanning electron. Instead of microscopy, we can say the nanoscopy, so that we can reach up to the nano world. Let's have a look on why someone need to study the SEM. How someone has to generate, or someone can generate the images by using this scanning electron microscope. These are the some important questions, and that need to be understand, or that need to be understand by the students, so that they will have a good information about their scanning electron nanoscopic picture. So let's have a look on electron beam sample interaction. What sort of interactions happens with electron beam as well as our samples? Then what are the different signals we are getting once the interaction happen in order to characterize our microstructures, right? So whatever the microstructures available in your specimen or sample, right, what signal you require to understand what sort of properties, right? So here usually people use the secondary electrons, backscattered electrons, and X-ray electrons. These are the three important signals detected by the various detectors and give you the important information about your materials, especially the nanoscale materials, right? And what are the important components of the SEM that already I had just briefed about. Then we'll see about the comments on the resolution, how the resolution of SEM can be improved, and what is the maximum resolution we can obtain from the SEM. And then later we will summarize this SEM part. So this SEM is having the very versatile instrument, especially for the material scientists, I can say. So what is the advantage of having this SEM system? First of all, the sample preparation of this SEM is very easy, very simple, right? You can have the bigger sample, smaller sample, the SEM is okay with that, right? So from the SEM, what we can get, what information we can get from the SEM is topography or a morphology, right? So topography of your sample as well as morphology, right? Then chemistry in the sense what sort of the elements are present in your sample. So that kind of chemical components we can easily identify by using this SEM system. Then we can look a little bit about the crystallography by using the SEM system. What are the orientation of the different grains? So that grains orientation also can be detected by using the SEM. Also, this SEM is very helpful technique to do the in situ experiments. For example, how your sample reacts to the atmosphere. Reaction with the atmosphere. Atmosphere, it means you can just induce something into the chamber and you can detect how this atmospheric or how the disturbance of this environment will affect on your sample, right? And also the effect of the temperature. So how this temperature get affected, on your sample. So these sort of information, simple information, we can easily obtain from these kind of SEM techniques. So for example, here you see the topography and morphology of these some samples here. You see one sample and this is another sample. So you here in this sample, you can see very good 3D picture, right? So 3D image from the top to the depth of this particular island. Let's say this is a small island, for example. In this small island, you can easily see the edges and you usually see the top and depth and everything. So it means this image is having very high depth of the focus, right? Until and unless you have the very high depth of the focus, it's very difficult for you to look into the deeper part of this, right? Deeper part of this particular island. Sometimes you can easily get only topography, only the topmost imaging you can get, but getting high depth focus is not possible by using the optical microscope. That can be possible by using the electron microscope because of the high resolution, right? So same thing here, you can see easily the small changes on the surfaces topographically. We can easily monitor here in this another figure, right? So this is the important application of this SEM imaging. So SEM world, nanoscopic world, we need to find out. So let's have a look on the depth of focus. Here you see the difference, clear difference between, let's say here is the screw which is having 0.6 centimeter of the depth length. Okay, so if this screw is visualized by normal microscope and if that same screw is visualized by the scanning electron microscope, you see the big difference. Here the image is clear only at the top or the topography of the surface, but here you can find out the image is very clear till the depth of this, right? So this SEM has order of magnitude better depth of focus than the optical microscope, right? And this is highly used for the rougher surfaces or uneven surfaces, right? Or various structures of the surfaces. So this kind of SEM can be easily find out the morphology of that given substances. So in case of the high magnification, if you improve the magnification of the SEM image, definitely the depth of focus will be reduced, right? So this is the another thing we will talk about, because sometimes we are not interested about the depth of the focus, but we are interested about the magnification of the image and to find out the small micro changes on that particular region, right? And especially in the nanoscale, we are more interested about the specific regions, but overall morphology also is important to know at which place you are what sort of changes are happening, right? So therefore this microscopic depth of focus is also important in certain applications. Okay, so let's have a look on the chemistry part. So as we have seen, this SEM can be used for the chemistry. Chemistry, it means here you see this is the specimen here at the first image, and then we have to find out what are the element presents in that. So this technique is EBSD or EDAX techniques, right? So many times people use as EDAX techniques. So EDAX techniques will be helpful. You have to just scan over the surface, given surface of the given specimen, and you can easily detect the elemental composition, elemental presence on that particular surface, right? So that can be also possible by using the SEM with EDAX, because you need to have that specific detector to get this. That we will talk later on. Okay, so this is another application of this SEM where we can get the EDAX pattern of this. Another one more advantage of having this SEM imaging is that we can do the in situ measurements or in situ imaging, right? So in case of modern nowadays, many SEMs are coming into the market, which are equipped with different in situ techniques. For example, the electrochemical cell measurement techniques. For example, electrical measurement kits, right? So there are several various techniques has been embedded into the scanning electron microscopy in order to do the different things, in situ measurements and in situ characterizations of the given system, right? So here, for example, you can introduce the hot stage, right? So instead of the normal stage, you just put the hot stage and you increase the temperature and see how your samples behave with change in temperature. Let's have a look on that example here. Here is the example of in situ imaging, oxidation of spill at very high temperature, for example, right? So here, let's say up to 800 degrees Celsius, the stage has been heated up to 800 degree, your sample has been placed on that is steel, okay? And then how that steel get oxidized with temperature and time, that has been seen in these images you see. So after 2 minutes, you find out there is very little or small white spots has been observed. After 10 minutes, there is increase of white spots. And after 90 minutes, 1.5 hours, you find out, nice grains has been formed on these surfaces, white grains. So oxidization rate is improved and formation of Cr2O3 is also possible, right? So this is how we can do the in situ measurements or in situ topographical measurements by using this SEM. Okay. So now that's fine. So what would be the basic about getting the image? How that image can get by using this SEM? Let's have a look on this electron. Once your electrons come in, incident on the sample, there are different signals coming out, right? So what are those signals? So what are those signals coming out here are the electrons and X-rays, right? So we have to shoot high energy electrons and we have to analyze what are the electrons and X-rays coming out from that system, right? So let's have a look on this instrument grid. This is the picture of normal SEM image, SEM instruments, which we are using in our laboratories. So here is the schematics where electron guns comes, it pass through the condenser lenses, electron beams. Then we have the scanning coils, objective lenses, and it can pass from that towards the sample, right? And these samples gives you, here are secondary electron, backscatter electron detectors. The signal received by this kind of scattered electrons get amplified and they display the image. They convert it into the image, right? And also the scanning coil has a magnification control, and that magnification control shows the scan generator, and it was given a feedback to this particular image formation. So how that image is formed? That is a simple question. So here let's have a look. Here is the electron gun, right? So electron gun, if you are putting the firing the electron gun, one small spot of the beam will appear on this surface, and then it can scan through this. Here is the small specimen, let's say this one, and here are the various pixels, right? So the spot size of your electron beam is, let's say, this much, right? So that spot size will scan over this surface from these pixels, right? Various pixels. So first of all, what happened? This beam will incident on the sample specimen in this quadrant, and then the electrons get emitted. Detectors will detect that electron, and there are 156 electrons. So the intensity of that particular electrons, frequency of that electrons, and then we can see here the small gray box is filled. So the small 1 pixel, right? So small 1 pixel is converted just by this spot. If you further move towards, another pixel, you can find out there is a similar action happen on that particular spot, and then you can find out there is a number of electrons, more number of electrons than generated, and you can find out how this shade has been changed. So color contrast has been changed, just changing the number of electrons received by the detector. Okay, and same thing, we have to just scan this complete beam or this specimen, and then we can convert all those things into the given region. Here you see here the number of electrons are changing, and then we are finding out these shades are according to the number of electrons generated and taken by this. And this is how this whole scan will happen on this particular region, and then we can convert this into the picture form, right? So this color contrast has changed, and this will generate the image. And these pixels are really very small pixels, depending on how much size of your electron gun, right? And the resolution, keep in mind, the resolution of any SEM will be highly depending on the size per size, right? And later we have to just use the different softwares to find it out. But usually the beam spot size, the resolution will not be more than that, right? So someone has to really work on the spot size. If spot size will be reduced, then probably we'll have the very good resolution of the system. Okay, so let's have a look what happened when your electron beam and sample get interacts with each other, right? So let's have a look. Here you have the electron beams. In the left figure you see here the electron beam with low accelerating voltage, electron beam at a medium accelerating voltage, an electron beam at a high accelerating voltage. And here you see the sample. So the depth of your beam interaction at low accelerating voltage is less. If we are increasing the accelerating voltage, the depth of interaction will increase. That is the one thing. So the scattering in the sample will happen both elastically and inelastically. So elastic and inelastic scatterings are happening if there is an incident of electron beam on the sample. And also this accelerating voltage is playing a significant role in the interaction specimen, right? So once this electron beam interact with the sample, we can get various signals, right? So interaction volume, so volume of the interaction here will be drastically increased with respect to accelerating voltage. But on the other side, this interaction volume of that particular beam will simultaneously decrease with increasing atomic number of that material specimen. So the specimen use some sort of the atoms, and what are the atomic numbers? So if your atomic numbers goes on increase, then definitely the interaction volume goes on decrease, right? So there should be the compromise between the accelerating voltage when you are using SEM scanning of your sample. Then in that case, you should keep in mind what is the atomic number of your specimen, number one, and then you have to think about the accelerating voltage. And then also you have to think about how much interaction volume you require, right? So there is a proper synchronization about the interaction volume, then atomic number, and then acceleration voltage, right? So these are the important parameters when we are talking about the electron beam and sample interactions. So what are the different signals coming from the interactions? As we have already seen before, there are the incoming electron scatters or incident on the sample, and it generates the backscattered electrons, secondary electrons, auger electrons, and then it can generate these rays of X-rays and cathodoluminescence light from this interaction of electrons with the specimen. So these are the different signals. So depending on what sort of signals you are interested in, we are using the different detectors and we are getting the different information about your specimen or sample, right? So let's have a look on this. So where does the signals comes from? From where the signal comes? You carefully see the figure over here, right? So this left figure, and there are the different color codes has been used for the different interaction part. For example, let's say here you have the incident beam. Incident beam interact with the sample here, right? So incident electron beam is given by the color this one, sort of dark pink color probably. This D is sort of resolution, right? So that resolution is so diameter of interaction volume should be definitely the larger than electron spot, because the electron plot defines your resolution, right? So it means your resolution is a little bit poor than the size of your electron spot, right? So it should not be smaller than the electron spot, the resolution, as I said just before. So here, this incident electron beam interact with the sample. So what happened at close to the sample surface? So here you see the incident electron beam. Here you see, so these are the secondary electron generated near. Later on, you will find out the backscattered electron region. Later on, you will see here. So this is the length, right? So this length, you are traveling from your sample specimen to deep into the sample. So you will find out very close to the surface. Probably there are the secondary electrons production. Later on, you just find out, you just travel some certain distance and you will find out the backscattered electrons were generated inside the sample. And beyond that certain length, you will find out there is a diameter as well as a length. So here, this volume or interaction volume will give you a sort of primary X-ray electrons, right? And then beyond that, you can easily find out the continuous radiations, continuum radiations in that system, and beyond that, cathodoluminescence excitations, right? So this is how these signals will be distributed throughout the specimen when there is interaction of the beam, right? So let's have a look on what are the secondary electrons. So secondary electrons, how they generated? First of all, your electron beam. In your specimen, you are having the various atoms, right? So atoms are having electrons circulating around it, right, in the external orbital. So what happened if your if there is a collision between the incoming electrons with the loosely bound external electrons or outermost electrons of that particular atom, right? So there is a collision that happens between them, and that collisions will give you, so after collision of that electron, it loses some energy, and very low energy electrons gets emitted from this, right? And those low energy electrons are having energy range between 10 to 50 electron volts. So they can be known as a secondary electrons. And those secondary electrons usually generated very close to the surface, right? Because the strength of the incoming beam is quite higher at the surface level, and therefore there is possibility to have the collision of outer bounded electrons in the atom with incoming electrons from the electron beam. So this situation of the secondary electron generation possibly occur at the very close to the sample surface. Okay, so if we want to have the very good topographic information or very nice topographic imaging, then these secondary electrons are playing very significant role, right? So what are the number of secondary electrons generated? So total number of secondary electrons generated at the surface is usually more than the number of incoming electrons, right? So there are electrons in the outermost orbital as well as the electron coming from the electron beam, and therefore this secondary electron generation is much more. And someone has to differentiate secondary electrons 1 and secondary electron 2. So what do you mean by the secondary electron 2? Let's have a look on the secondary electron 1 first. As we have seen, that secondary electron that are generated by the incoming electron as they enters on the surfaces, right? But we can get a very high resolution signal limited by the electron beam diameter, as we have already discussed. But what are the SE2 secondary electrons? So that secondary electrons usually generated by the backscattered electrons. So those backscattered electrons return to the surface after the several inelastic scattering inside the specimen. So there are the several atoms inside the specimen, deeper inside the specimen. And once your incoming electrons goes, if it's not collide with, let's say, if it won't collide with the surface atoms, then it will go to the deeper atoms, and in the deeper atoms they can have the interactions, or they may not have the interaction. They have the interaction at one of the deeper atom, and then they release the secondary electrons and they reach to the surface, and that is called as a secondary electrons, or it is called as a backscattered electrons, right? So that Se2 comes to the surface area, comes from the surface area, which is bigger than the spot from the incoming electrons, right? And therefore the resolution of this secondary electron 2 is quite less than the normal secondary electron or primary secondary electrons, right? So what are the important factors which usually affect on secondary electron emission? So the important factor is that what is the work function of your surface? So how this work function of the surface, if the work function is low, then if work function is high, then the secondary electron emission. So work function, low work function, it will easily emit this, right? So the beam energy and beam current is another important factor which affects on this secondary electron emission. So those electrons, what happen? Electrons goes through maximum when you have the low acceleration voltage, right? And it decreases with increasing the accelerating voltage. Here you see this figure. Next, this is the incident electron energy per kV and secondary electron yield, right? So secondary electron yield is very high at a low accelerating voltage, right? So electron yield goes very maximum at the lower. But if you further increase the acceleration voltage, then you find out there is a decrease in secondary electron yield with respect to increasing the voltage, right? So initially at the low accelerating voltage, you find out very high secondary electrons, right? So therefore, if you want to have the very good topographic image from the SEM, usually we need to have the very low accelerating voltage, right? And therefore there is a probability to get a very high secondary electrons, and therefore you can get a very good topographic image by using this low accelerating voltage, right? So further important factors, as we have already discussed before, there's atomic numbers. So those atomic numbers which can, if you increase the atomic numbers, these secondary electrons too are generated more, right? So there is a several interaction inside the atoms, and then you can find out this secondary electron too, right? So this atomic number is more pronounced at the low beam energies, right? So if your beam energy is very low, then this Z plays a significant role, right? Also, the another important factor for the SE emission is local curvature of the surface. If your surface has the low curvature, then the topmost surface SEM emission will be very high. So the pointed surfaces will give you the good SE emissions, right? So these are the important factors which we need to understand about the secondary electrons, right? So if someone wants to have the very good or high resolution image setup, in that case, what we have to do is, or what microscopist or operator has to do is, they have to simply place a detector, secondary electron detector inside the lens, right, where exactly your SE1s, so secondary electron ones are coming. In the path of the secondary electron one, we have to just place the detector, secondary electron detector, and you will get a very good resolution of that particular image, right? And that resolution is possibly 1 to 2 nanometer. Okay. So further important thing is backscattered electron. So those backscattered electron, for example, BSE. So if the fraction of incident electrons, here you see in this figure, fraction of incident electrons get retarded by the electromagnetic field of the nucleus, right? And if the scattering angle will be more than the 180 degrees Celsius, then electron can easily escape from the surface, right? It will just come and get deviated by the electromagnetic field and it will come out, right? So this is how we can get the backscattered electron. So those electron did not interact much and then come back from this region. So this is, and this region is this one here, you see here. So the high energy electron, these are nothing but the high energy electrons where we will have the elastic scatterings. But what happened, if you compare with the secondary electron and backscattered electron, usually the backscattered electron as compared to secondary electron are less, right? And secondary electrons are more in case of SEM system. And if someone wants to use this backscattered electron for certain applications, we'll talk about when we have to go for the backscatter imaging and secondary electron imaging. There should be the differentiation between the backscattered electron 1 and backscattered electron 2s as well, right? So this region, just now we were talking about this region where we have the backscattered electrons. So these are the types of the backscattered electrons. As we have already seen, there is a scattered electron 2, and similar thing we can find out the backscattered electron 2. So how this backscattered electron behaves as a function of atomic number? As we have seen, the Z plays a very significant role in SE. Same thing in BSE. We'll find out the Z is very important. So if you increase the Z, we will find out the backscattered coefficient is more, right? So increasing the backscattered coefficients with increasing the atomic number of the given material, right? Given specimen. So what are the important factors? Same like as SE, there are some factors which affects on the BSE emission. For example, let's have a look on the direction of the irradiated surfaces. If there are the more electron hitting on the BSD detector, right? When your surface is aligned toward the BSE, so your surface has to align towards the BSE electrode, then only, or you have to tilt your specimen so that you will get a more BSE detector images or more signals to the BSE detector. In that case, you have to just tilt your sample a little bit and get the BSE images. So why that BSE images are important? Why that SE images are important? When we look into the dark field, bright field imaging techniques of this microscopy, that time this SE and BSE is playing very significant role. High energy and low energy is also important to give the good imaging of the system. Also, we need to know the average atomic number of the system, which also affects on BSE emission, right? So if someone wants to study the difference in atomic numbers of the given sample, vice versa, we can also identify the atomic number of the sample. But it's quite challenging one because you have to level the sample very accurately, right? And that probably the sample preparation would be the major issue if you want to measure the atomic number by using the SEM imaging. So here you see the clear difference between the BSE, the upper image, backscattered electron detector image, right? And image processed by the scattered electron, right? So you see here secondary electron and backscattered electron. So you can clearly identify the difference between the image. So this image, SE image, is giving more information and very high depth and very clean image by using the SEM. But if you have the BSE, this image is not so clear, and so the contrast is not very good, right? So that's why this SE is highly preferred. SE is highly preferred for the SEM image. Further important thing was the X-ray, and in X-rays we are not using the electrons, we are using simply the photons, and that photons can be detected. But the spatial resolution is quite poor in case of the X-ray as compared to your backscatter as well as secondary electrons, right? So the very poor resolution by the X-ray, and relatively this X-ray will take, these X-ray signals coming from your specimen will take longer time. Therefore, you have to bombard electron beam for longer time on your sample, and long bombarding time on the sample probably will damage your sample, right? So this X-ray scanning is very important, and that has to be time-consuming process, because X-ray signals take some time, and probably it is inefficient, and very low signals will be collected over a longer time. So these are the limitations to find out this, but X-ray will give us the information about the composition of specimen. Okay, so what is the commonly used detector in this kind of X-ray is like EDS, so energy diffusive spectrometer. So this is a very common spectrometer, is used in, as we have seen in photograph of the SEM, where EDAX system has been placed, and most of the EDAX systems are using the energy diffusive spectrometer. But here another problem is the single overlapping of these different elements is another problem with this system. So we can analyze the sample by using this X-ray using the different modes. For example, you have the spot analysis at that particular spot what elements are present, or you can have the line scan so that you can find out at which region which element is rich, or you can have the elemental mapping over the surface what you have selected for the imaging, and then as we have seen in the previous images, right? So what has to be considered when you are using the EDS? So if you are using the EDS system, the date time, right? So date time means how long you have to bombard the beam on your surface is very important, and the delay between getting the signals, X-ray signals to the detector and bombardment, so that date time is very important, and that should not be more than 20 to 30%, right? Further, the signal to noise ratio, because your beam, if beam energy is very high, in that case you will have the very noise signals, right? So if your beam energy is low, then it further takes delay the process, but at the same time the signal to noise ratio is improved, right? Further one is the drift in electron beam with the time. If you consistently bombard beam on one spot, single spot, then you will find out there is a little movement of the electron beam. After certain time, then there is a drift of electron beam can observe on the surface. So the position, localization position cannot be the same if the drift is there with the time. So within a short span of time, if it's possible to get the signal from the X-ray, will give you the more ideal information about the specimen. So further, if you do this process for the longer time, then they can build a contamination just by burning the sample or creating the carbonese contaminations over a period of time, and then probably it will reduce the resolution also, right? So how that can be removed, that will be seen in the further. So let's skip this component of the instrument. Already we have talked about this. So electron gun, just a brief introduction about the electron guns. So what are the ideal electron guns? That how many number of electrons per time unit per area is given. So simply in simple words, it should have the very high current density, right? And a very small spot size, because the spot size will also affect on your resolution. So there are the various guns people are using in the different systems. The traditional gun is thermionic electron gun, where electrons are emitted when your solid gate hits. For example, here tungsten wires or lanthanum hexaborate crystals people are using, right? So in modern days now, people are using the field emission gun. FEG. It is called as a FEG, field emission gun. So that is relatively a cold gun, but it needs very strong electric field to extract the electrons, right? And in this kind of field emission gun, usually the single crystal of tungsten is being used. So tungsten is to a very thin tip, so the emission will be very sharp at that particular thing. And here are some pictures just for your sake of understanding. It is very difficult for us to go and see inside the system how those kind of beam guns looks like. But here you can easily see the single picture in the picture, the single crystal of LAB6. Then here you see the tungsten wire, which is connected between the two, and very high voltage will generated across these two, and this electron get generated from this. And in FEG gun, so this field emission tip, that is a tungsten tip is there, and so that tungsten tip's diameter is it's around 1,000 angstrom, right? So this will emit a high current density electrons, right? So this is simple electron guns people are using. Here is different detectors people are using to detect the signals coming from your specimen after bombarding the electron beams. So for example, here you see the backscattered electron detectors here, where usually solid state detectors people are using for this application. In secondary electron detectors, here this is shown as the secondary electron detectors, right? So Everhard and Thornhill has developed one of the secondary electron detector that is a very standard people are using in almost all the systems. And in X-ray, as we have already discussed, that EDS, which has not been shown over here. So sometimes people will be worried about why this electron microscopy needs more vacuum, right? Because electron microscopy without vacuum it's not possible. And why we need a vacuum? Because in normal optical microscope we are not using any vacuum, right? So why in electron microscope we have to use the vacuum? So first of all, the chemical corrosion should not be happen, environmental issues. Secondly, the thermal stability, which is very necessary for well functioning of your filament or gun pressure. So your gun pressure is very important to extract the electrons. Also, as soon as your electron gets detached or electron gets lived from that particular electron beam, then that has to travel to the detectors, through the sample to the detectors. So that electron should not get deflected by the external entities, and therefore these should be in a vacuum, right? So field emission gun usually requires 10 raised to minus 10 torr of the pressure, vacuum pressure inside the chamber. And especially this field emission gun requires more vacuum as compared to lanthanum hexaborate tip, right? So lanthanum hexaborate requires 10 to minus 6 torr of the vacuum inside, right? So vacuum requirement is also depend on what type of the detectors you are using, as we have seen the various detectors before. So depending on the detector, we need to know this SEM. So we have seen that SEM, different fundamental aspects of the SEMs. Now, I just want to elaborate something about the environmental SEM. There is another important class of the environmental SEM. What is the difference in normal SEM and environmental SEM? So this environmental SEM, traditionally that SEM chamber pressure is 10 to minus 6 torr. So that is in traditional SEM system. But if you go to the environmental SEM system, the pressure is reduced and it comes to the 0.08 to 30 torr. So very low pressure, vacuum pressure inside the chamber, and that SEM gets operated under the various gases, as well as it requires the different SE detectors. So what is the advantage of having that low pressure SEM images or low environmental? Why it is called as environmental SEM? Because it has this very low vacuum, right? So what is the use of having this SEM? ESEM. So ESEM is important to image the challenging sample. For example, insulating sample, right? Insulating sample, it's very difficult to get image from the insulating sample as we are passing the electron beam, right? So in that case, if we have the insulating sample, then the electron will not go towards the ground and a lot of electrons will stay on the surface, and there is a charging effects happen on the image. And because of the charging effect, it's very difficult for us to detect or take the see the topography or take the image capture the image, because those beams, because of the charging effect, will not steady on the surface and it will start deflecting on the sample surface. So those deflection of the image will not properly give you the required signals to the detector. And therefore, most of the time during the specimen preparation, people are talking about the coating, conducting coating on the insulating sample, so that you can see the morphology of that insulating sample. So to avoid the charging effect, we need to have the coating, in conducting coating on the surface. So most of the insulating samples will get coated. Even the semiconducting samples, to avoid the charging effect, we need to coat it on the conducting, thin conducting coating has to be done in order to ground the electrons, excess electrons generated on the surface. Okay, so in the ESEM, what we see is the vacuum sensitive samples. For example, there are a lot of biological samples, right? So those biological samples, vacuum probably may not survive at very high vacuum. They may not survive, right? And therefore the sampling is the one issue, and another is imaging, right? So to have the biological sampling, imaging, we need to have the ESEM, right? Or thin organic films. So irradiation sensitive samples. If you bombard electrons, then there is the irradiation happen on the surface. And another important thing is wet samples. For example, you have the oil and greasy and dirty samples. So in that case also ESEM will help you to give the good imaging, right? So what is the important things which can study, or how we can image the chemical and physical processes in situ in this case of ESEM? So in case of ESEM, mechanical stress testing can be done, right? So you can do the mechanical stress on your sample and you can find out the deformation, all right, on your sample by using the mechanical stress testing. Further, the oxidation of the metals. If the oxidations happens, because if you have the less vacuum, then there is a possibility to form the oxidation on the surface. And how that oxidation happens, that in situ oxidation can be seen by using the ESEM. Okay. Further, the hydration and dehydration, for example, watching how your paint is getting dry. Right. Once you put the paint on the sample stage, and if you put inside the SEM and you see how that paint, getting dry, that in sort of that kind of studies can be done using the ESEM. Another important thing, these are the instrument, different accessories of the instruments people are using. I don't want to go into that at this moment. But nowadays, there are very fancy tool people are using is dual beam SEM. Dual beam SEM, it means there are two different beams in a single SEM chamber. One is ion beam and one is electron beam. So electron beam will use for just measuring the morphology or seeing the morphology topography of that particular specimen. But this ion beam will help you to pattern your specimen or pattern your substrate, either etching or deposition of the different things. So this will be very helpful for nano device or nano electronics or a lot of further applications, or patterning and writing, making the marks on different areas at a nanoscale. So that kind of embedded or multi-purpose dual beam system, SEM system, is nowadays used by the various researchers, especially the nanoelectronics and other part of this community is using that sort of the SEM images. So how the best resolution can be obtained by using the SEM? First of all, the size of electronic spot. So that size has to be controlled in order to get the more resolution, right? So in fact, what we observe that field emission gun, we observe very high resolution as compared to tungsten or lanthanum hexaborate. And then volume from which the signal electrons are formed also defines the resolution, right? So the secondary electron image has more resolution as compared to the backscattered electron image, right? Another important factor on the resolution is the scanning speed, right? So weak signal requires very slow speed, right? But in order to improve the signal to noise ratio, right? So when we are doing very slow scan, we can observe the drift in electron beam with respect to fraction of time, fraction of milliseconds, and that will definitely affect on our analysis. Okay, so these are the important factors which need to be keep into the mind about the electron microscopy. So scanning electron microscopy just now summarize this scanning electron microscopic part, and then we will move to the TEM part very rapidly. I think we have more than half hour, so we can cover the TEM part at least. So the scanning electron microscope is a versatile instrument used for the many purposes, right? And that resolution of that particular is 1 to 2 nanometer, right? And therefore we can call it as a nanoscopy when it operates at very high resolution set, right? It can go up to 1 to 2 nanometer resolution by this one. And ESEM as well as the field emission gun have simplified the image of the challenging samples. As we know, these are the different signals, and from what signals, what information we can get is, let's say for example, the secondary electrons, mainly we can get the topography image. From the backscattered electron, mainly we can find out the chemistry. So, and X-ray also gives you the important information about the chemistry, but it's take the longer recording time and probably it may damage the sample. Therefore, this X-ray is time-consuming process. So these are the different summary of this scanning electron microscope. Here we see the SEM different image of, let's say here SiO2 spheres. Here you see there are the very good spheres, right? But the spheres sometimes you can find out at the curvature there will be not be very clear curvature, but the surface is very good. So how can we make this image more beautiful, right? So what sort of corrections is required while measuring this or while imaging these kind of samples, right? So here you see the succulent plant, and here you see these edges as well as these curves and everything is very sharp. So why there's such a big difference in this curvature and this curvature? Why this curvature is giving you a very beautiful picture as compared to this? Let's see that one after one. So here you see the hair split, and here you see this is the darker point, bright points here, and that has been just brightness is observed because of the charging. If we would have do the coating of the conducting material, probably we should have avoid this kind of excess brightening on this sample. Here you see the bug's eye SEM image can be also seen by the ESEM most probably. And here are some of our images from our research groups. Let's say here, this is V205 flower, which is having very good high depth imaging. So three-dimensional and very nice image we have observed over here. As compared to this image, here you see this is the MnO2 rods. So flower of MnO2 rod. As compared to this image having 1 micron scale here, and this is a 2 micron. But see here, the depth of this is much better than depth of this, right? So if you maximize it, we can find out there are the various rods assembled into the flower, and these rods we can see here, right? So the 20 nanometer we can easily see there are the transparent rods over here, right? So delta MnO2. So this is beautiful and fancy tool to take a pictures at the nanoscale. So nanoscale photography or nanoscopy is highly essential to get such a beautiful images at a nanoscale, so that you can get more information about your sample or more information about your material. So here you see this is the nano rods. Here you see the flower assembled because of the sheets. So these are the nano sheets, right? So sheets and then rods, and then you can easily see here the tubes, right? And after taking the images, these images can be processed in various processing softwares. For example, ImageJ. ImageJ is one of the software widely used to just process the images, and so that you can add the colors in your SEM images. Or this is just a contrast, right? So use the contrast to give the color. Okay.
Sound echo होते थोड़ा split होते हैं.
Okay, so I can maybe reduce the volume so that echo will not come to you. Okay, so this is beautiful imaging done by the SEM especially, right? And high depth SEM imaging, high resolution SEM imaging, and identify what sort of images are there. Okay, so let's have a look. If we want to have a very good imaging, see this sort of imaging, right? Very high depth and very clear imaging, what needs to be done in case of electromagnetic lenses? What are the abbreviations that electromagnetic lenses can do, right? So let's have a look on, there are the 3 important aberration corrections are required in electromagnetic lenses in order to get a very good image of your sample. So first one is a spherical aberration, second one is chromatic aberration, and third one is the astigmation, right? So these are the 3 important corrections need to be done in electromagnetic lenses so that you will get a required image, or you will get a beautiful imaging of your sample. So here is the spherical aberration. The spherical aberrations usually occurs because the normal lenses are very powerful at the corners, and at the centers you are not having that much power of that particular lens, and therefore from this corner what happens is the focal point is missed, because at the corner this lens is very powerful, and this focal point will not be adjusted, and it meets just before your lenses, right? So this is just a problem, and how this problem can be solved is by using the disk of the minimum confusion, right? So the minimum confusion, how that minimum confusion can occur? That minimum confusion can be occur by using this one. So here you see the disk of minimum confusion having the diameter which is d is equal to c upon alpha cube. So this alpha is the incident ray, right? Alpha cube of this incident ray. So what happens is we have to reduce this alpha value in order to get the large reduction in the d, right? So get the high resolution. So we need to reduce this value. But in case of optical one, this is the reverse. In optical case, the incident angle should be the more, as we have seen before. But in the microscopic case, we have to have very low incident angle in order to get the large reduction in the D. Right. So this, what is the average alpha value is 10 raised to minus 3 radians, and which can take us to the 0.1 nanometer. Right. So this is the important thing for the spherical aberrations. So how the spherical aberration can be avoided by just minimizing the fluctuation, confusion of this. So later we can find out the chromatic aberrations. So what is the chromatic aberration? Chromatic aberrations here we find out because of the changing wavelength of incident light. So incident light wavelength changes, and because of change in wavelength, your focal points are changing, right? So focal position are changing. And because of this change in focal positions, you are not able to get the correct images, right? So how to overcome this kind of incident beam or light of the different lambda, right? So this lambda can be controlled, this wavelength can be controlled by fixed potential, different potential difference used towards the gun, right? And the lens current which is passing through the electromagnetic lenses. So these are the two important things we need to control in order to control the lambda value, right? But as soon as these electrons incident or interact with the specimen, it will change the lambda, right? So what should be the thumb rule in this case? So chromatic aberrations, how it can be done is your resolution should be greater than or equal to the specimen thickness divided by 10, right? So almost 10 times specimen thickness. So the resolution, so 10 times resolution your specimen thickness should be. It should not be much more than that. Okay, so that is how we can do the chromatic aberrations in order to get the proper imaging. Okay, so this is another corrections. So another correction is spherical and chromatic aberrations. So the last one is astigmation. So astigmation is usually occur because of unsymmetry. What do you mean by unsymmetry? Because your lens, let's say, are more powerful in only one plane. For example, here your lens is very powerful in this plane, right? And another side the lens is not that powerful, so there is a mismatching of the focal points here, you see. So here the lens is powerful, so it is mismatching to this. Here is, let's say, focal point, but because of the powerful lens you can find out this, and the mating here just far away from the focal point, right? And then you need to have the minimum confusion, right? And the asymmetry should be reduced, right? And in that case, how can you control the asymmetry of this? So this asymmetry will be caused just, there is a 90% deflection, and you can try to meet this point over here. So here what we are doing is just image as a short line where we can flip through the 90-degree. So this is the strong signal coming from this strong plane, and that has to deflect by the 90 degrees and focus with the minimal confusion, and then it can reach up to the focal point, right? And that's how the astigmation has been occurred. So how the astigmation arises? So the astigmation arises because just of inherent geometrical defects inside, right? inside, for example, the circular bore of your lenses. So inside the lens, there might be probably geometrical defects, right? Or there is probably inhomogeneity in the magnetic properties of the pole pieces, right? So your different pole pieces we are using, so they may have the inherent inhomogeneities, right? So these are the certain important points need to be understood about the astigmations, right? So, and again the charging effect, there is another charging effect because of the contamination on your pole piece as well as your aperture. On the aperture, what happened? Non-conducting deposition may happen. So usually, what happen to have the good estimation, what microscopists are usually doing is after certain time, after 2 to 3 hours of use of this particular or 1 to 2 day use of this microscope, they have to do the cleaning, self cleaning, alignment and focusing of this particular system, because there is the contamination, the resolution has compromised and astigmation effects has been generated inside the system. And to avoid that, regular servicing of your beam as well as lenses as well as alignment and focusing is required to get a very good image, right? So therefore the astigmation is nothing but a time dependent process. So over a period of time, definitely the astigmation will occur in your system, and that cannot be shorted out. That is by default the process, right? And therefore continuous correction inside the system is required to avoid the astigmation. So how the astigmation correction can be done? There are two important things. One is the glass optics, right? So you have to just use the proper glass optics, astigmation correction, so that what happen, the addition of the lens will avoid the asymmetry, right? Or you can use the electron optics. In the electron optics, electrostatic astigmation will give you the strength and the asymmetric directions, right? So it can stop the asymmetry in the directions. So only the objective lenses need to be corrected accurately, and that correction is good, even after 1 or 2 hour continuous use of this particular thing. So these are the three important corrections everyone has to do to get a very high resolution image, right? So depth of the focus and depth of profile we have already seen. Let's have a look on the TM now, because SEM, as we have seen, has a resolution up to 1 to 2 nanometers, right? But if someone wants to go beyond that, beyond 1 to 2 nanometer, someone has to use the transmission electron microscope or transmission electron nanoscopes. So in transmission electron nanoscopes, what we are usually doing, I will just keep this basic information. Here, this is a general picture of the TEM, and where we have to place sample on the copper grid in order to help your electron beam to transmit through the sample, because the transmission requires enough energy of electrons. It has to pass through the sample and the specimen generation. So sample preparation for this TM is quite delicate as compared to the SEM. SEM, you can use the bigger sample, that's not a problem. But in the TM, we cannot use the bigger sample. We have to have the thin sample, thin enough sample, so that this electron gets transmitted to this. And in order to help those electrons to transmit more faster from the sample, this kind of the conducting grid is required. Usually people use the copper grid, and where we can put our specimen or sample on this, and we will pass this electron, right? So in order to transmit those, here are the general images of the TEM. Here this SiO2, and here these white dots in this figure in organic material. You can see these are the atoms. So atomic resolution, single atom can be seen by the TEM imaging. In SEM image, it cannot go up to the single atom, because atomic range is very less than 1 nanometer, 0.4 or 0.3 nanometers probably. So this is not possible just because of SEM, right? So what we have to do is the TEM analysis. So TEM is nothing but the shadow image, because in SEM we are using the backscattered electrons or scattered electrons, right? But here in this transmission electron microscopes, we are transmitting electrons through the sample, and we are collecting those transmitted electrons on the fluorescent screen, right? Therefore, we are getting the shadow image of your sample. Okay, so here the gun, this is the standard things. Gun emits the electrons. Then we need the electric field to accelerate the electrons to go through. And we have the magnetic and electric field control of path of electrons using the different electromagnetic lenses. But here, in order to work the TM electron wavelength, here 2 into 10 raised to 12 meter, if we use the 200 keV, and electrons can operate from 100 keV to 400 keV. So there are the variant version of the transmission electron microscopes are available. If you go to the higher higher potential difference from, let's say, 200 to 300 to 400 electron volts, you will find out the wavelength of electron can be going down and down, right? And then you can improve the resolution. So here, with, let's say, for example, 200 keV electron, the resolution limit is up to 2 angstrom. So someone can go up to the 2 angstrom limit when they use this kind of TM with 200 electron volts, because this potential difference U, remember the first formula, lambda is usually depending on V, right? So this V is this one, and that lambda wavelength has been tuned, right? So that has to help. So when electron hits the matter, what is happening? We have already seen the electron interaction, that is secondary electron, backscattered electron, and all those things we have already seen. So I don't want to repeat those things over here again, but I just want to see that, if you are hitting the electrons, for example, all those 3 electrons simultaneously, if it are hitting, then what happens? So there will be the collision on outer shell of electrons, which either removes or insert the electrons in the system. Then in that case, what happens? The free radicals formation may occur on the sample surface, right? So these chemical species are quite active in that sense, right? Therefore, the reaction with your neighboring atom induce the massive change inside your specimen, right? If you have the very light atom, for example, it's very difficult for, just to bombard that high potential difference or highly accelerated electrons on that lightweight atom and get the shadow image of that, right? So that particular radiation severely damage the possibility of having electron transmissions, right? So therefore, the examination of biological samples or cells in the live state is not at all possible by using the electron beam, or in case of TEM. Inside the TEM, at least by using the ESM, you can do the sampling of the cells, but using the TM, it is not at all possible, because the radiation will severely damage that living cells and they will become a dead, and then you will find no information from that, right? So these all examinations, probably with a low dose, probably people can try out, but this low dose may or may not work in this case. So fourth one, what happen if your electron doesn't interact or collides with your specimen, and it will be unchanged and transmitted electrons, which can be used for this kind of imaging in TM, right? And this is usually called by the subtractive contrast, right? So subtractive contrast, because there is no interaction of your image with specimen, just transfer, so the shadow image can occur. And these transmitted electrons can be collected or can be fall on these kind of different cameras. For example, the CCD, TV or TV type camera screen. On the screen, they bombard and they can be converted into the image. Or they can be placed on the photographic film, and direct impact of the electron on photographic film will give you the imaging of that particular sample, right? So usually the silver halide grains detected virtually by every electrons are probably the 50x of more efficient than photon capture. So this kind of transmission is 50 times more efficient than the photon capture. So the beam damage, when it occurs, if there are the light elements which lost very rapidly as soon as it bombard on the sample, right? So there is always change in valency may occur because of the free radical forms during the interaction of these atoms with the electron beam. And then chemical reaction generally occurs. For example, using the TM, many times people are able to find out the melting points of the given substance. So in order to understand the melting point of that, you have to easily calculate what is the dose you are giving to the sample, and at what dose, what sort of the temperature will generate on the surface of the sample. And then you can easily find out the melting point of that particular sample, melting or boiling point sample can be TM, but that is very delicate. It's really to understand the properties of that. But the beam damage can be minimized using the low temperature. For example, in 2017, the cryo transmission electron microscope has received the Nobel Prize. So why the cryo is required for the sample, especially the biomolecules? At low temperature, the beam damage will be drastically reduced, and that will help us to do the imaging of the biological samples. Then we need to improve the high beam voltages, and we need to have the minimum exposure dose in order to avoid those things, right? So these are the different this is a picture of our TM system, which is having a 300 kV system, and which has a resolution up to few angstroms, let's say 3 angstroms or so. Here are the different components of the electron beams. I don't want to go much detail about this, but just have a look about the TM analysis. So what sort of the TM analysis can done by using the TM imaging? So this is a TM of WO3 nanorods. Okay, so this you see here, these nanorods are randomly or overlapped on each other, so it's very difficult for our beam to pass through and get this proper shadow images. But if you focus on other part of the region, you can clearly see here these are the edges, facets, right, on this edge. So these facets in the shadow images can also be very seen properly. So this is the edge side, and here on the surface side. So if you little bit improve the magnification, you can clearly see here there are the porous network on the surface, right? So how that porous network, so these kind of TM imaging can be taken for the simulation, and after the simulation we can extract the more information about that particular specimen or particular sample. Here in case of this W3 nanorod, what we observed is, let's look at the surface. If you go on the surface and maximize it, you will see there is a little porous network and orderly organized the pores, right? So this order organized pores here, you can see here in this inset, these are the pores. So pore size can be detected here. This D image is nothing but inverted Fourier, fast Fourier transform imaging. So inverted fast Fourier transformation image can give you what are the pore size, what are the shape of your pores, right? So this is sort of hexagonal pores, and there is let's say 0.614 nanometer of the diameter can be clearly seen by using the IFFT image, right? Further, we can further zoom on another part of this particular region or on the surface or edge. We can easily find out here, you see, there are the different lines. So the arrangement of atoms and interplanar spacing can be easily detected by using this particular TM imaging. And here in the inset, you can see the FFT image, and that FFT image can give you, difference between these two lines, and that is interplanar spacing between these two atoms. So we need to index. So here you see here another IFFT image of this particular surface will give you the proper lines. But here you observe carefully, these lines are distorted here in this region, right? So here in this region we find those lines are very clean and very straightforward, but here in this region we have found out these lines are not clear. So there is some distortion. What is that distortion? That distortion is nothing but the crystal defects, right? So what sort of the defects are there? So the understanding of the defects inside, is there the line defects, is there the point defects? So what sort of defects are there? That information of your crystal defects can be also detected by using the TM imaging, right? And here you see this is very important thing, that is SAD pattern, selected area electron diffraction. So this electron diffraction pattern gives us more information about the crystal structure, orientation, arrangement, and in order to understand this different selected area diffraction pattern, we need to look into the various systems so that we can understand how this selected area diffraction will give us more information about the crystals, right? So this is how this TM, the transmission or shadow imaging of that nanoscaping, nanoscale materials are very important. Right, let's have a look on some of these important things. Here, another one TM image of our MnO2 nanorods and nanosheets. So here you see the rods, and here you can find out the different lines, and we can easily, by using the TIFFT image, we can easily find out the thickness of that individual atom, right? So size of the atom and then separation between these two. Here you can see another side pattern image. So there is the difference between the previous side image and this side image. Here we find more ring structure, and in the previous case we have found out more dotted structures, right? So single crystalline and multi-crystalline nature can be easily differentiated by using this kind of side patterning, by using the TM image. Also, we can have this kind of scanning, elemental scanning on the given surface of the TM. Inside the TM also, that can be possible, same as what we did in SEM. Here there are more hybrid structures. Let's say, for example, here is a carbon nanoanion wrapped by different MnO2 sheets, right? But is that sheet is a single sheet or multi-layer sheet? So in order to understand that, just focused on that age of this sheet, and we can find out there are the number of layers of the sheet, right? So this is not a single MnO2 sheet. There are number of sheets assembled together, and there is almost 7 to 8 sheets come together and wrapped around this CNO material. So this kind of imaging also has been done by TM. So you see how beautiful this TM technique is. These things you may not find inside the SEM, because SEM has the low resolution up to 1 to 2 nanometer. If you want to go beyond, for example, if you want to see how many number of layers over here, what is the thickness of the individual layer, so that cannot be possible by using the normal SEM imaging, right? And therefore we need to go, if you want to go more deeper into the nano world, you need to do the TM analysis. So here are some of the different images of TM. Here you see the dislocation in superalloy can be easily find out by using the TEM image. These are the quite older images, but yeah. So the sample preparation is a key in TEM analysis. So in the TEM analysis, if we need to really get a very good imaging or very good information of your material, then preparation of the sample is very important issue. The sample should be thin enough, so as thin as possible. So thinnest sample will give you more clear image and more clear information about your material, right? So here, different types of samples can be used. For example, you can use the films, slices, powders, and foils, right? So that has to be thin enough where, ultra microtomy, and you have to do different crushes and dispersion carbon. So these are the different specimen preparation techniques people usually used. For example, they use the grinding, then use the etching, then use the ion sputtering. In order to get, this is the ion sputtering image of the thin film. You have to just make hole and just tilt your sample to find out what is happening in this edge of this, so that you can understand the thin film information at this particular region. So this is another important specimen preparation. So what important here in the diffraction pattern, as I had just said, that diffraction pattern shows the different for the different samples, right? So what it makes the difference? So as we know the Bragg's law, where lambda plays very important role, right? And your lambda is much smaller in case of the TM, as we know that, because we are using a very high potential difference. So we can easily reduce the lambda value here, right? And then we can find out the resolution is up to 2.5 angstroms, right? If your incident angle is 0.2, so very small incident angle here. So how can someone find out this particular interplanar distance? For example, this d value, here is the formula, right? So lambda 2d sine theta, and where we find RL, L is the camera length, right? So this is the specimen, and your graphitic, or this is the screen, and then your specimen, and then that distance, probably the camera length. And then these spots were in scattered diffraction, you will find out in the diffraction pattern, you find the different spots, and that spot distance from your straight camera point here, that can be measured, and from that you can easily find out what is the d value, because you know the L value, you know the 2 theta value, and you know the R value. So we can find out the interplanar distance between these two spots, right? So these interplanar distance calculations will give us the information about the planes and arrangement of the atoms and structural information of your material. So here are the different important diffraction things. Yes? Is anybody talking in between? Or okay, so I think I have to wind up in next 5 minutes. Is it? Uh, Dr. Bhaskar, how long I have to be continue? Probably, I don't know.
5 minutes.
5 minutes is fine, right? Okay, so let's have a look on the diffraction pattern. The symmetry of the diffraction pattern, which reflects usually the symmetry of the crystal around the beam. Usually, 6 folds in hexagon and 3 folds in the cubic. Here you see here the hexagonal and cubic. But the question arises, why does the 3-fold diffraction pattern looks like a hexagonal, right? So that question is need to be the answer. For example, here you see these are the different patterns, and usually all the diffraction patterns are centrosymmetric, right? Even if your crystal structure is not a centrosymmetric, your pattern is a concentric, and that was given by the Friedel's law, right? So in that case, what happened? If your zero level pattern, you can exhibit the higher rotational symmetry, that your structure has. So your structure should have the rotational symmetry, and therefore the 6-fold and 3-fold as the rotational symmetries in that. So here is some of the diffraction patterns you can see. These are some important examples, but I can skip these points. Edward construction is also okay. I have to show you one of the important example how this indexing is also fine. So once you know this, let's say you have the diffraction pattern, you can simply find out the distance between these consequent neighboring spots, and you can find out the R1, R2, and R3 values. Then by using the formula which we have already seen before, by using that formula, you can find out the D values, right? D is interplanar spacing D1, D2, and D3 in the specific plane. And then these values you can compare with, let's say, for example, these D220 and 440 values are 1.4 and 0.8. And if you see these values are here, or the distance between these two are matching with those D values, then you can simply index those spots, right? So indexing of the spots is very important. So index other reflections by using the vector sum or the difference formula, right? For example, here you have the zone axis, and where you can do the cross product of any two and then find out the indexing of diffraction pattern, right? So indexing of diffraction pattern is very important, right? Which can give you the information about what sort of the crystal structure, lattice parameters, and indexing patterns can be there. But let's move further. Why the indexing, which will give us the detection of epitaxy, orientation relationship at the grain boundaries, and so on, right? Here the polycrystalline. Why polycrystalline? Because there are the various crystals. One crystal is in this, another crystal in this form. So there are multiple crystals together can generate this kind of ring structures, right? So that we have already seen in one of our MnO2 sample, right? So these ring structures, usually we know the distance between these rings. So the larger ring will have the high resolution, and lower ring will have the low. So this is clearly indication of this. And from this D value, we can easily index the plane of these individual rings. So this is the how we can do the indexing. So I don't want to go into now the bright field and this all dark field imaging technique of this TM. But this dark field and bright field imaging will give us a lot of information, as we have discussed about the general microscopic thing. And also these dark and bright field imaging together, we can find out the lattice imaging. And in order to do the lattice imaging of the given sample, we need to do the simulation, right? So we need to have the simulation or structure simulation, so that we can easily match this pattern with your simulation, right? So this is how these different diffraction pattern of the different sample can be seen. Here, this is just one of the important point I want to emphasize here is, this is not exactly the crystal structure. This is the pseudo crystal nature of this organic material. Or let's say here is the ALMN system, for example, which is showing here the sad diffraction pattern. But if you are changing the angle, tilting the angle of the sample, if you tilt and do this kind of scattering measurements, you will find out there is a change in diffraction pattern. And this is just because there is a solid, rapid solidification happens in this alloy by just tilting the grain with a different side. So this is very beautiful tool people can use and play with that to understand. So this technique will be used by different people to understand the non-crystallographic structures of non-crystallographic systems. Okay, so this is how atomic force. I don't want to go now with these atomic force microscopes. As we know, this atomic force microscopy is one of the important, where we are using the probe spectroscopy to understand there are the various modes like tapping mode and contact mode, non-contact mode, and so on. So with this, I think I need to summarize this talk. So let me skip this STM as well. Okay. So there are different STM techniques also used to align the atoms on the surface, right? So this is showing that iron atoms on the surface where we are just pushing the atom by using the probe technique. So that probe is used to align the different atoms on the different surfaces. So this is the beauty of STM system. And okay, I think these are the different types of the microscopy and why we have to use the different modes of microscopy. Today we have gone a little bit more fundamentals about scanning electron microscope and that's application into the transmission electron microscope as well. With this, I think I need to conclude here today. So this microscopy is a fantastic tool to see the nanoscopic world, and from that we can get more information about the chemistry, crystal structure, and we can do a lot of in situ studies about our nanoscopic sample. With this, I would like to acknowledge my research group, my colleagues and director from our center, and my collaborators, especially the Professor Sathe, Professor Latte, and so on. So with this, I would like to thank all of you. Thanks for your kind attention. So I think I will be ready for the questions. Yes, Sade, any questions from the audience or? Shall I see in chat box if there are any?
Very excellent talk, Pravin sir.
Thank you, but it was more informative for the students as compared to the researchers. So I hope the students get benefit of this.
Yeah, sure. Check any questions in a chat box is there or not.
Yeah, I'm checking why there are a maximum in secondary electron only at the low voltage. Yeah, actually, I have already shown one slide where the secondary electron intensity with respect to the potential. So at very low accelerating voltage, we have found out the maximum number of secondary electron, right? So intensity or frequency of the secondary electrons is very high at the low voltage. So why that is maximum, that need to be checked, because low voltage probably takes longer time and have more interaction time with the specimen. If the high voltage, then acceleration of your electrons probably high, and therefore instead of preparing the secondary electron, it may go to the deeper part of the specimen and it can generate the more backscattered electrons, right? And therefore the secondary electron generation is possible at the low accelerating voltage, because the low accelerating voltage plays significant role on the surface itself. The interaction on surface is more because of the low voltage, right? If the accelerating voltage is high, then interaction on the surface probably less and it can penetrate to the sample, and backscattered electron generation will be high as compared to scattered electrons. So how to differentiate metal nanoparticle and non-metallic nanoparticle with the microscopy? So with the microscopy, if there are the non-metallic nanoparticles are there, you will find out definitely the charging effect on the surface. So a lot of electrons come on the surface, and then there is formation of electron cloud on the surface, and therefore the charging effects will be there. Or sometimes you may not get any sort of image because of the charging, excessive charging. You may not get any image, right? But in metal nanoparticle, there is a grounding of electrons happen, and therefore the signal generated from the surface will be very good. And in that case, you will find out very nice images of metal nanoparticle. So this is how we can easily find out the metal difference between the metal and non-metal nanoparticles. Okay, so anything else? Yeah, in the TM, whether it goes interaction with chemical group attached to the nanocrystal. Yes, definitely. Definitely, as we have talked about, this TM electron interaction can happen with everything, whatever in your specimen, right? So chemical groups definitely get affected by the electron, and if there are the organic group, probably because of the high energy, there is a bonding issue may happen, right? So the loosely bound atoms can easily break by this kind of excessive energy given to that particular bonds, and definitely there is chemical reaction happen, or any kind of chemical group attached to your surface get hampered by TM. I can share one of the experience from our side, because when the Cipla company had given one of their sample iron nanoparticles coated with the sucrose, right? So in that case, it was very difficult for us to identify the sucrose coating on these iron nanoparticles. It was very easy for us to find out the iron nanoparticle present inside that solution, but the sucrose coating was not possible, and therefore we have used another technique to understand the total diameter including iron and sucrose coating by using the, let's say, scanning probe microscope. So we have used AFM techniques to find out total diameter including iron nanoparticle and sucrose coating, and then we use the TM to find out the normal only diameter of this iron nanoparticle, and then we can easily subtracting those values, we can easily identify what is the coating of the carbon is. Okay, so what else was there? Chemical group. In case of pharmaceutical nanoparticle functionalized with chemicals, how to identify attachment of such chemical group by TM? No, it's quite very difficult to, it's very difficult to find out the functionalized part, because as long as you have the organic material is fine, but if you are going to the inorganic material, if you go to the organic or biological, it get interacts, as I said, it gets interact with the electron beam, and it's really difficult, as I given you one of the example of sucrose, right? So that is the important.
Pravin, sir, stop now. I will
Yes,
share you
yes,
your
I think
ID
that's fine. Yeah.
participant.
Okay, thanks a lot.
Anybody having any doubt, then they will contact you directly.
Yes, yes, sure,
Okay.
definitely. Thank you very
Because
much. Yeah.
already we extended to 30 minutes more. Okay. Thank you very much for your valuable talk, and definitely participant will get benefit by uh, the characterized techniques which you are having at your center. Okay. Thank you. Thank you
I
again.
welcome all of you anytime if you need any characterization from our time.
I'm very much happy by your talk today, because I'm first time I'm listening.
Oh, thanks a lot.
Okay,
Platform
then.
now.
Yeah, I will stop this
Meeting
session
now.
now.
Yeah. Oh, fine.